So we are beginning a new chapter that will be different than pretty much anything we've done in the beginning year of chemistry. It's on chemical kinetics. And in kinetics, we study quite simply the rate at which a chemical process or reaction is going to occur. Not only will we look at the speed at which they occur, we'll also look at the steps or the mechanism that is called, showing exactly how the reaction is going to occur. In this particular vodcast, I'll be talking about concepts such as average rate, instantaneous rate, and relating concentrations to the stoichiometry of the reaction. Specifically, that refers to sample exercise 14.1, 2, and 3. So at the conclusion of this vodcast, or at any time, you need to complete before Monday morning those sample exercises by simply copying them into your lecture notes where space has been provided. I will not be going through those problems in this podcast with you now. So let's take a look at the factors that do affect reaction rates, and some of this should seem familiar from last year. One of the factors is the physical state of the reactants. We call this the collision model. Particles have to collide, they have to collide with sufficient energy, and they have to collide at just the right orientation with each other. So for molecules to come in contact with each other, basically we're saying that's a lot easier if they're in the same physical state. So gas molecules bumping into other gas molecules is more probable than, say, a gas molecule bumping into a solid. So the more homogeneous the mixture of the reactants, the faster the rate. Another factor that we studied last year was the impact of concentration of reactants. As you increase the concentration, the greater the likelihood that particles will collide, the faster the rate. And so what you're seeing there is some steel wool being burnt or set to heat up in a Bunsen burner, but when plunged in an Erlenmeyer flask that is higher concentration of oxygen, you get a more rapid rate of oxidation. A third factor clearly is temperature. Most reactions at higher temperatures are going to react or occur faster. That's because higher temperatures mean greater average kinetic energy of more of the particles, so they're moving faster, they're more likely to collide with each other more frequently, and the energy with which they collide is greater energy and more likely will have the possibility of having sufficient energy of collision. We learn that as activation energy, and we will study that again. Finally, the last factor is the presence or absence of a catalyst. A catalyst will speed up a reaction by changing the mechanism of the reaction. A specific example might be a catalyst might act as a go-between between two reactants and link up part A with part B by acting literally as the middleman. A lot of catalysts are solid metals, and they provide a surface where molecules can sort of roll into position to react with each other more readily. The key concept of a catalyst is that at the end of the reaction, it emerges unscathed and unchanged. It's not part of the chemical reaction. It just facilitates that. Therefore, it will help the reaction to occur more quickly. Now, the real focus of this chapter is we're first going to define reaction rates and end tonight by understanding what order of a mechanism is and how to recognize a first-order reaction. If you look at this sample problem that you see here, we have time equals 0 on the far left, showing that we have all of A substance and none of B. Now let's say A can turn into B over time. Well, 20 seconds later in the middle beaker, you can see that there's almost a 50-50 mix of A and B molecules. And 20 seconds after that, now the B molecules are dominating in concentration. You can calculate the reaction rate by either figuring out the change in concentration of a reactant as it disappears or a product as it appears. In this particular set of data, you can see that butyl chloride reacting with water can turn into butyl alcohol or butanol and hydrochloric acid. So we have what we call our initial time and initial concentration of the butyl chloride. Now we take measurements every 50 seconds. And if you measure the concentration of butyl chloride at various times, like we will be doing in our crystal violet lab, you can find the average rate, since rate is the amount of concentration change over a change in time. by simply finding the difference in concentration in one time period. So you could find the difference between 1 and 0.095. That would be the change in concentration, and the change in time would be 50 seconds. You started at 0, you ended at 50. So the average rate is calculated by taking the change in concentration of that reactant over the change in time from one step to another. Now you can do that for each one of those steps. And if you look closely, as the reaction progresses, it seems to be slowing down. The rate is getting less and less. The rate unit in this particular problem is measured in molarity per second. We'll look at various rate units in a moment, but the reason that the rate slows down is because you're consuming those reactants. So there's fewer collisions, and therefore the rate will go slower and slower because they're being turned into the butyl alcohol. So if you were to plot that, you get a curvy line. Time is measured on the horizontal axis, and the change in concentration of that reactant, butyl chloride, on the vertical axis. Notice that the rate at the beginning, which can be measured by taking the tangent to the curve at any point, so the instantaneous rate right here would be a tangent to the curve, that is pretty steep. You let some time go by. Now we find another instantaneous rate at 600 seconds, right about there. That's where you can have the slope of a line tangent to the curve that will be able to determine the instantaneous rate. Remember, slope is rise over run, so it would be change in concentration of the methyl chloride or butyl chloride at that moment divided by the amount of time that had elapsed. So rates slow down, and we have a lovely curvy line which doesn't do us much good. And what we're going to see is that some people smarter than me have used calculus to straighten these lines out and to integrate and make use of a straight line expressing various reaction rates. And we'll talk it to you in a moment about how to do that. So all reactions slow down over time. The best rate to measure would be the instantaneous rate near the beginning of a reaction. Now, as I said, there is a sample exercise, and that would be 14.2, that has to do with calculating instantaneous rates. Please copy that down in your lecture notes. So you can finally also relate the reaction rates to stoichiometry. In this particular reaction, the amount of the butyl chloride is in a 1-to-1 ratio with the butyl alcohol. So you can measure either the disappearance of the butyl chloride or the appearance of the butyl alcohol or butanol. Notice that if you are measuring the disappearance of the butyl chloride, you put a negative sign in front of it because it's decreasing in concentration. And to find the rate based upon the change in concentration of the butyl alcohol, that would be a positive number. But if your ratio is not 1-to-1, as expressed in this reaction, where 2 hydrogen iodides make 1 hydrogen molecule and 1 iodine molecule, or mole of molecules, now what we have is a different situation. And the way that this rate is being expressed is you will take the inverse of the coefficient preceding either each reactant or each product. So that's why there's a 1/2 in front of the change in concentration of hydrogen iodide over the change in time. There is a 2 as a coefficient in front of the hydrogen iodide, and we're going to put a negative value in front because we're looking at that from the perspective of the hydrogen iodide disappearing. You could measure the rate based upon the appearance of iodine. This time, notice there is no fraction in front of the change in iodide over change in time, or time, because the iodine is appearing, not disappearing. It's a positive value. So in a generalization, if you have an equation that looks something like this, where the small letters represent the coefficients, the rate could be expressed as the negative of the inverse of little a or little b multiplied by the change in concentration of the reactant A or reactant B, each divided by the change in time. The positive values for the change in concentration of C and D products is found by taking 1 over C times a change in C, or 1 over D times a change in D over time. Remember, brackets around these capital letters represent molar concentration of. So you can express a reaction rate either in a negative sense or a positive sense. But what we can really gain information about and how these rates were determined experimentally as well as the rate constant is you conduct an experiment and see how the rate changes with changes in initial concentration. This is a classic type of problem. You will run a number of trials in the mythical world, and also in the real world we'll be doing this. And what you will be doing is holding perhaps one reactant constant in its concentration while varying the concentration of the other reactant. And when you do so, you can see what impact that has on the rate. So let's look at that first example. You always have to compare two trials to each other, and one of the trials has to have the concentration of a reactant not changing. So ammonium ion and nitrite ion can become nitrogen gas and produce 2 water molecules. So in reaction 1 and 2, or in trial 1 and 2, they've kept the NO2 concentration constant. It's 0.200 molar. But they've doubled the ammonium concentration from trial 1 to trial 2. And the impact of doubling the concentration of ammonia is that it will double the rate. You can see that this number is twice as big as that. If you look at another trial, like trial 5 compared to trial 6, this time they are varying the nitrite and keeping the ammonia concentration the same, but doubling the nitrate concentration. If nitrite doubles, so did rate. So both of these reactants seem to have an impact on reaction rate. The rate, therefore, is proportional to both the ammonium ion concentration as well as the nitrite ion concentration, and this can be rewritten into a law that we call the rate law. And it looks something like this. You'll have rate equal to a rate constant, and the rate constant is expressed with the letter K, times the concentration of ammonium times the concentration of nitrite ion. Both of those, by manipulating them, impacted the rate. So that's what we call a rate law, and specifically ammonium and nitrite are both what we call first order. Now let's talk about what that means. The exponents that you would have to the upper right of the concentration values tell you the order of the reaction with respect to each reactant. So since our rate law looks like this, see how there's unwritten ones that are here in the, where did my cursor go? Okay, here he is. See how there's unwritten powers of 1 up here? We're saying that the rate is first order with respect to ammonium and first order with respect to nitrite. First order means that if you double that reactant, you will see the rate double, assuming you held the other reactant constant in its concentration. So that's what we call a first order type of reactant. But if someone is asking you what is the order of the reaction overall, you simply add the exponents. So they're not shown here, but there's a 1 to the upper right of the ammonium concentration, a 1 to the upper right of the nitrite concentration. 1 plus 1 is 2. So based upon this actual trial which was conducted, we call this a second order overall rate law. Now what you can do to clean this up, remember that curvy line versus straight line thing I alluded to a little while ago, you can take the natural log of the concentration at some time divided by the concentration of your A at time equals 0 at the start. That's equal to the negative of the rate constant times the time. Now I know this looks new to you, but you'll get comfortable with it. Mathematically, you can manipulate that equation, and I don't need you to worry about the derivation at this point, but eventually you get an equation that looks like this. And hopefully it looks familiar to you. The natural log of the concentration of reactant A at a specified time is equal to the negative of the rate constant times that specified time plus the natural log of the concentration of A at the beginning. Y equals mx plus b. And as we all know, that is the equation for a line. And if your reaction is first order, the way you can take the curvy line where rate is changing and turn it into a straight line is by taking the natural log of the concentration of reactant A. And it looks something like this. We might have this methyl isonitrile turning into acetonitrile, and here's its curvy line version. The rate is faster near the beginning, the rate slows down towards the end, and it's best probably to take my rate closer to the beginning. But we collected this data at 198.9 degrees. First thing, don't let the temperatures change because that will obviously impact the rate and the rate law constant. So we always specify that. Now that's not helping me with that curvy line, that's that calculus thing. So I'm going to plot this graph, not with the pressure. This was acetonitrile, so it was measured as a gas. You can use either partial pressure or molarity. In this case, they had pressure as the unit of concentration. But if you take the natural log of that reactant's concentration, then your line becomes a straight one. And in this particular place, it's a negative slope. That's why there was a negative number in that original equation. So whenever you take the natural log of a reactant's concentration plotted against time, and the line comes out straight with a negative slope, that is definitely how you identify a first order process. And the K would be found, the rate constant, by taking the negative of this slope. So if I had measured between any 2 points on the line, probably farther apart from each other might be better, and I take the negative of the rise over the run, I get this interesting rate constant, 5.1 times 10 to the negative 5 seconds to the minus 1. That means per second. So a change in concentration per second. So those are called first order processes, and that's mathematically how we're going to manipulate them. I will hold off here and take up second order processes when we meet next. Until now, please make sure that, or until then, please make sure that you complete those first 3 sample exercise problems.